Hello everybody, my name is Eduardo Tominaga. I'm a doctoral researcher at the University of Oulu, and in this video I'm going to present our new journal paper. The title is Performance Analysis of MIMO-NOMA Iterative Receivers for Massive Connectivity. This is an open access paper. It was recently published in the IEEE Access Journal, and the link for this paper is on the description of this video. In this picture, we can observe the scenario considered in this work. We envision massive machine-type communications in beyond 5G and 6G networks with data aggregation. The mMTC devices transmit data to gateways that perform processing tasks, for example, data compression, and then forward information to a base station. Owing to power, size, and cost limitations, the gateways cannot be equipped with a very high number of antennas, and for this reason, the number of active devices that they serve can surpass the number of receiving antennas. So the research question that we address in this work is how to provide wireless connectivity in an uplink scenario where the number of active devices is higher than the number of receiving antennas. Our proposed solution is the combination of multiple input, multiple output, and non-orthogonal multiple access techniques. We propose a set of iterative MIMO-NOMA receivers that can decode multiple overlapping signals for any number of active devices K and any number of receiving antennas N. So we utilize both linear techniques, like linear receive combining using maximum ratio combining, zero forcing, or minimum mean square error receivers, and non-orthogonal multiple access with successive interference cancellation decoding or parallel interference cancellation decoding. We compare the performance and complexity of the following schemes: the linear receiving combining techniques, MRC, zero forcing, and minimum mean square error receivers, the nonlinear techniques with SIC decoding, MRC-SIC, ZF-SIC, MMSE-SIC, that decode only one user at each iteration, and also the nonlinear receive techniques ZF-PIC and MMSE-PIC that decode multiple users at each iteration. As the performance metric, we adopted the outage probability, and as the complexity metrics, we adopted the average number of SIC operations and average number of matrix inversions. So here we first present the results for the case where the number of active devices is equal to the number of receiving antennas. So here we have 8 active devices, 8 receiving antennas, and a target data rate equal to 1 bit per second per hertz. And we plot here the outage probability, the average number of matrix inversions, and the average number of SIC operations versus ρ, which is the transmit SNR per antenna. And in this situation here, we observe that the ZF-PIC and MMSE-PIC present the best performance for the whole range of ρ. And now we have the results for the case where the number of active devices is higher than the number of receiving antennas. So we again have 8 receiving antennas, but now we have 20 active devices and a target data rate of 0.5 bit per second per hertz. We again have the plots of outage probability, average number of matrix inversions, and average number of SIC operations versus the transmit SNR per antenna ρ in dB. We now observe that the only receiver that can achieve a satisfactory performance is the MMSE-PIC receiver, but this performance is achieved for only a specific value of ρ that makes the outage probability achieve the optimal value. Thank you very much for watching this video. Please check our open access paper that is available in the link on the description, and please subscribe to our channel.